Hey, welcome to Ether Cosmology. This is the Ether Roundtable number 14. Tonight I'm going to talk a little bit about the twin paradox because we've talked about that a few times over the last few weeks and I just kind of want to go over it. Also, I was presented with some more information about it. And then Alan's going to do a deep dive into GPS and we're going to talk a lot about C plus V, C minus V, aka the quote unquote speed of light is not constant. It's relative to its inertial frame. Let me go ahead and kick off the Discord event here, and then I will share my screen, and we can get into the twin paradox. All right, I'll give everyone a second to tune in to the presentation. And then if everyone's ready, I'll go ahead and move on. So you guys can all hear me, right?
Yes, sir.
Awesome.
Ready when you are.
Cool. So this is going to be a presentation about the twin paradox. And essentially, we are living in Albert Einstein's thought experiment. Here he is, the man himself, Albert C. Einstein. C stands for clown. And let's get into his work on the electrodynamics of moving bodies. This is what he published in 1905. This is essentially the birth of our modern interpretation of the theory of relativity. So he says here that the unsuccessful attempts to discover any motion of the Earth relatively to the light medium suggests that the phenomena possess no properties corresponding to the idea of absolute rest. And then he says they suggest rather that the same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. And then further down, this is actually still on page 1, and so it's interesting because when you talk to a lot of people about this, they will pretend to understand relativity, but then they will make arguments that are actually in contradiction to page 1 of on the electrodynamics of moving bodies. And so here we go down to, it says here, the introduction of a luminiferous ether will prove to be superfluous inasmuch as the view here today to be developed will not require an absolute stationary space. And then he says, nor assign a vector or velocity vector to a point of the empty space in which the electromagnetic processes take place. And then just moving on here, so here is him deriving C as a constant, and he gives his example. He uses an atomic clock example here, and then he says, thus, with the help of imaginary physical experiments, we have settled what is to be understood by synchronous stationary clocks located at different places, and have evidently obtained a definition of simultaneous or synchronous and of time. The time of an event is that which is given simultaneously with the event of a stationary clock located at the place of the event, this clock being synchronous and indeed synchronous for all time determinations with a specified stationary clock. And then he says, in agreement with experience, so when he says this, he's only referenced, at this point in the paper, all he's referenced is his imaginary physical experiment about the clocks. And then he also referenced that we didn't measure any motion of the Earth. There's only two things he's mentioned. So that's what he says is in agreement with experience. He says, we further assume the quantity to be a universal constant, the velocity of light in empty space. So here's more of him deriving it. C is constant. So he has the equation there, and then he says, it follows from this equation that from a composition of two velocities which are less than c, there always results a velocity less than c. So you know that old thing about like 2 plus 2 equals 4? Well, what he's kind of telling you here is that 1 plus 1 doesn't equal 2, right? 1 plus 1 will always be less than 1, as long as the, less than 1 plus less than 1. Even if it's 0.9 plus 0.9, always going to be less than 1. And then he says, it follows further that the velocity of light, c, cannot be altered by composition with a velocity less than that of light. So this is going to be, keep this in your mind when Alan starts going through the GPS stuff. This is
These are the rules.
These are the rules. This is the groundwork for relativity and special relativity. So then in 1913, Paul Lavant comes along, or Lanvin comes along, and he says, basically he's saying experimental facts that have recently been established have shown that if the equations are valid for one group of observers, they must also be so for all others, whatever their motion relative to the first group. And then he says, this leaves us with the paradoxical fact that any given light wave must travel at the same velocity for different groups of observers in motion relative to one another. So if you're in motion and someone else shines light at you, and you are somehow magically moving almost as fast as that motion of that light, then somehow time has to change so that you immediately, you have a proportional, that constancy of c is relatively constant for you and for them. So instead of just accepting that the light may or may not be constant, which has been demonstrated, and we'll get into that, you just have to go back to the rules. And then he says here, for the second group of observers, that the light wave will still be moving with respect to them at the same velocity of 300,000 kilometers per second. And then this is funny. He says, Einstein was the first to demonstrate how the necessary consequences of electromagnetic theory can by itself. It's funny he says demonstrate, because we just went through how he quote-unquote demonstrated. He literally called it a imaginary physical experiment. Yeah, so now let's talk about the actual twin paradox, right? Because I don't remember when I first heard this. I don't know if I'm assuming most of us here are familiar with it. I tried to actually find where it first came up at, where this particular thought experiment came up from, and I wasn't able to hunt it down. It sounds like it was probably some physics professor at some university somewhere that, was just trying to wow his students and sound cool. But in any case, this is the implication. This is called the twin paradox. So basically, you've got two twins on Earth, both the same age, right? They were born the same day. And one twin decides he's going to become a space traveler, and he's going to travel to a distant star. So he gets in his little rocket. As the space traveler nears the speed of light, because his rocket's going real fast. If you're going to go to a star that's, 4 light years away, you don't want to spend your whole life going there. But as he approaches the speed of light, their relative time slows down. So in his little rocket here, his time is actually slowing down because he's going too fast for that light to keep reaching him at the same rate that he would be, say, emitting it. Let's say he was shining a light out to him, right? So, his relative time is different than his. And then as the space traveler returns home, he finds that his twin has aged significantly more than him because remember, his time slowed down. His time stayed the same speed, quote unquote. But however, if time slowed down for the space traveler, what was the time shift relative to? Was the time shift relative to an absolute frame? Because there can't be an absolute frame of rest. We just went over that. This actually is a paradox, truly. Because relativity has to say no, but we live in an absolute frame, and all observation, all of our experience in life shows this. And this is someone named David pinged me on Telegram with this quote from Gerardus Bau, who was a PhD astronomer, and he says, since in a truly relativistic framework, these two conditions are identical, who actually will have aged? And so, that's a good question, and that's, there is kind of an implication here of an absolute frame. Now, they try to what's the word I want? To make this
their way out of it.
They try to get their way out of this. They try to say they have an explanation. And here's going to be Ron Hatch is going to talk about. He talks about this argument put forth by Ohanian, and I didn't actually go through and find Ohanian's argument about this because I just didn't have the time. But essentially, I did see a couple videos with laying out this argument. Essentially, all they really can do is come up with a covariant equation of how the time dilation occurs relative to each observer. That's the best they can do, and they use the idea of acceleration to be their differential, and they say that because the person on Earth is not in the same acceleration frame as the person that's going to travel to the star, that somehow resolves the paradox, even though the person that comes from the star will still be a different age when they get back. So really, it's just some mathematical explanation, but it doesn't actually solve the paradox, and that's kind of what Ron Hatch lays out right here. And he says at the bottom, he lays out, so the hyperbolic rotation effect is a general effect. It does not depend on how Terence and so if you read about this, there are a lot of people will use the names Terra and Stella or Terence and Stella. Terra is the one that stays on Earth. Stella is the one that goes to the stars. It does not depend on how Terence and Stella become separated, only upon their separation distance. Thus, the same effect should be observed by measuring the amount of time a distance pulsar loses or gains when an acceleration toward it is executed. If the effect were real, it would be easy to see. Ohanian's solution to the tick-tock paradox does not work and cannot be made to work. He failed to follow the implications of the solution to its logical conclusion. And then just to close things out, I'm going to just touch on a quick quote from Robert Bennett in his paper, the 1905 relativity paper, Analysis and Obituary, where he basically just goes through that exact Einstein paper that we started with and dissects it. And actually, I would recommend, if anyone hasn't gone through Albert Einstein's on the electrodynamics of moving bodies from 1905, I would recommend doing that, because I had only actually glanced through certain portions of it before this, and having spent so much time thinking and meditating on these things and diving into the research on these things, to then go back and look at this paper was very enlightening for me, because this is the groundwork, right? This is essentially the foundational document that our high priests in this world that we live in are forced to, this is their religion. So we should understand this. As incoherent as it is, we should be able to, dismantle the incoherence. And then let's just read this quote from Robert Bennett. He says, Maxwell's theory is only tested in the lab frame. Validity in other frames of reference is assumed via the concept known as frame independence or covariance. But when the conductor is not in the lab frame, Faraday's law is invalid. This is consistent with Newton's bucket test. The water vortex is only predicted by the centrifugal law applied in the lab frame. And then, if imaginary physical experiments, so just to make it clear, imaginary physical experiments don't explain reality, and you shouldn't need a PhD such as Robert Bennett to explain that to you. But sadly, I think a lot of us did need that. And that's all.
Dude, awesome presentation. And yeah, like towards the end there, so when they get into their solution for the paradox, right, they say, oh, well, we got a covariant solution, right? Well, that's the danger with covariance, right? Like, it's a hell of a drug. It doesn't actually have to mean anything, because as they pointed out, that paradox isn't manifested, right? Like, it's not
and it's still a paradox.
And it doesn't even absolve anything. And the implication of absolute space to be the reference to for the disparity of who actually aged, right?
Yep.
So it's really interesting when they say it's like a thought experiment. It's like, well, that's why when you do real experiments, like your logical inconsistency that you didn't realize, gets weeded out really quickly. So like they can only talk about the twin paradox by showing you, a movie like Interstellar and presenting it that way and like blowing your mind. And it's like, oh my God, he's older than his daughter. He's younger than his daughter now. What? That's so crazy.
It's so cool.
But it's like, yeah, like, oh, no way.
Literally said the phrase imaginary physical.
Yeah. Well, there's a more eloquent phrase in German. They call it like something else where it's, it has a little more prestige to it, I guess.
Gudeskin, I can't remember what it is.
Yeah, like Guggenheimer or something, yeah. Like, or whatever. Volkswagen Jetta. So, all right.
Question, Toby.
Yeah, what's up?
So, equally absurd, and this isn't even to do with the math, even though, it's a math thing that they're trying to solve the paradox for. But, like, the suggestion that you would age backwards with an acceleration in an opposite vector, like, to think that biological processes would move, chemical reactions would move because of an acceleration vector, like, what?
Well, to be fair,
Period.
they don't say you would age backwards because they can't actually do like a true covariance like that, right? Because they were, I guess, smart enough to not try and imply something like that. But like what they do say is that you would the relevant time difference at like they all they do, they call it a solution, but all they do is factor in the math for the change in vector when the person turns around to come home from the star, and then the change in velocity there. And all it means is that time goes fast, or there's more of a time slowdown as they're heading away, and then as they're heading back, time actually speeds up for them relative to the person on Earth. But they still end up being way older than the person on Earth when they get home.
Yo, was that where that was didn't Einstein said that in a paper, and he didn't even like show the math for it. He just said that the calculations show it, and then didn't even show the math, bro. Like for the exact scenario you're talking about for the return trip,
Something
because
tells
they need
me.
to
Well,
because they need
I
time to
saw a
double
couple
back,
people
right? Like
try
it's
and do the
insane.
math. I wonder if he was talking. Yeah, I wonder where
Uh,
that math especially like first did come from. I wouldn't be surprised if Einstein just made it up in his head and then pretended
yeah,
like it's out there.
he didn't even attempt it. See what he got clowned. It's ridiculous because it would you couldn't make the determination without an absolute frame to determine who actually aged.
There's a TED
Like it would
video
just
about it, and I like I hardly doubt that they would have checked the source.
I think
dude,
even though it's an elementary point, I think it's important and relevant to mention just for because you might have people from all comprehension levels in the audience for this topic that the whole reason that they're trying to like manipulate time is because velocity equals distance over time, and velocity wanting to be fixed as c and distance wanting to be fixed as a known distance. The only variable left that they can change is time. So they only have three variables they can manipulate. That's why they have to do this time magic, essentially.
yeah, that's why. Yeah, the gamma correction, like the Lorentz correction, is applied to the time axis and the x-axis, and the x-axis is the direction of motion. So those are the only two options that they could change to keep the speed of light the same as Piso was just saying. They can track the coordinate system that they're describing the motion through proportional to hyperbolically to meet c, so that they can say it's the same. And then when they do the math on it and the transformations and it lines up, they're like, "Oh, no way, relativity."
They summon Time Magician and roll a 6.
Yeah, dude. Oh no way, I found relativity right where I was looking for it, dude. I found length contraction right there. It was there the whole time. All right. So with that being said, we'll go ahead and get into GPS and its in relativity and its role in GPS. So GPS is a time interval system that uses a range measurement equation, and by the end of this presentation, hopefully everyone will know exactly what that means. So the first part, we're going to break down the time interval system, right, which gets into the atomic clocks, how that functions, how GPS keeps time, and then we'll get into how they utilize that with a range measurement equation to get exact distances, uh, similarly to what Piso was just talking about. So here's the atomic clock again for reference. We have a link to a YouTube video here if you want to check out the full video. It's about 40 minutes. It was a really interesting video. They go through this atomic clock, boot it up, synchronize it, go through the whole process, walk you through it, tell you about the ins and outs. I'm going to give you the quick TLDR on it, so should be shorter than 40 minutes, hopefully. So there's just a couple extra pictures of the atomic clock, the equipment there. Here's one without the case open, so you got the whole chamber here, a bunch of electronic components. We'll get into what all that does, right? So the way they describe how this clock works, they say it's using cesium, right? So with cesium, they say that due to its what do you call it, atomic structure, that it has one valence electron. So in their model, they have it modeled out where they say that on the outer rim here, on this outer ring, there's one electron, and they can manipulate that electron and analyze it and do all this cool stuff that they say or whatever, right? But that's how they explain it, right? So I'm going to explain it slightly differently than an electron orbiting a ring, a singular electron. So they have their cesium oven here where they house their cesium. They heat the cesium up; it turns into a vaporous gas. The vaporous gas gets channeled out. Once it's coming out, It enters this magnetic field here, and any of the cesium that's vibrating at a faster rate than its natural 9.192 gigahertz rate, it bounces that out. So the next part of this is a resonance a radio wave cavity. So they have the cesium trapped in here that's vibrating at 9.192 gigahertz, and then they start shooting microwaves at that cesium. Once they hit the same resonant frequency, um, and they've matched the cesium's vibration, they use that as their calibration to send that out to an ionizer. So as they're leaving the chamber here, they exit another magnetic field, and that field will use electromagnetic retardation to bounce out um, anything that's not matching that 9.192 gigahertz frequency. Once that cesium gas and microwaves hit the ionizer, it gets converted into electric energy, which they put in this electron multiplier, which is just like an oscilloscope. It's just bouncing the current back and forth and amplifying it so that they can get a reading out of it. Now, when they get that reading, they're like, okay, this is what this pulsation rate, like this matches, um, that oscillation rate that they're looking for, that 9.192 gigahertz frequency. So when they have that, um, they do you guys hear that, or is that just me?
I think it's just you. I don't hear anything.
It's driving me crazy. Give me 1 second. Okay, hopefully that's it. All right, where was I at? Okay, so once they get their 9.192 gigahertz frequency locked in, where they've matched the cesium, it they lock in how much like radio frequency they're putting in, right? And they use that to keep time. So once they have that synchronized and set up, they can split 1 second down to 9,192 millionths of a second. And they just keep that in a loop essentially, right? So that's the baseline for how this clock works. These aren't in the right spot. Okay. Okay, so when we get into Einstein synchronization for these clocks, so what do we do with these clocks now that we can split time into uh, 9,192 millionths of a second? What do we do with that? Well, now we need to synchronize these clocks with moving clocks so that we can set up a network, right? So, according to mainstream physics and and the correctness of relativity theory, they tell us that the proper way to sync a clock is to Einstein's theory of relativity. And the way to do that is you would have a stationary clock here in a frame, in a distance between them at a length, what do you call it, L sub s. Then you'd have a clock B over here in this stationary frame, right? And then you would have your moving frame, clock A or clock alpha and beta. Clock alpha and beta would be moving across a stationary frame. At the moment alpha and A intersect, alpha sends a signal to clock B with its time that it's sending a signal, and a half-time correction for the half speed of light. So this clock synchronization depends on the speed of light being the same on the one way and on the bounce back. So they use this half-time correction to modify how long it'll take for the propagation to get there, so that these will be in alignment. So this clock activates, subtracts that half-time from that, and then these should all be in proportion. If they're not for some reason, it'll reference back to clock A. Any corrections will be made to get A and B on the same time, and then they're in sync. They from that hypothetically they should be in sync in perpetuity, right? There should be no further corrections needed. But what they found through Heffel and Keating and through experimentation with moving clocks, they found that the clocks go out of sync to varying degrees, and ultimately what they found is that they have to correct them proportional to the velocity of what's carrying them. So the results of the original Heffel and Keating, the clocks were way out of bounds on their readings. It actually gave a null result, right? Like you wouldn't go into battle with these results. It took it in their first published paper. They were way off. Yeah. So yeah, you're good. So they analyzed their results, right? This is from their 1971 unpublished paper that had to be FOIA requested to get it, right. So they said this is from a transcript from them giving a debrief to the military who funded this experiment. So they say the results in the analysis are in a reasonable agreement with the theoretical predictions. However, those who doubt the validity of the convention of relativity theory, and there are many people in this category will probably not be converted by the results shown in Figure 4. Indeed, the difference in theory and measurement is in Figure 4 is disturbing, and our final analysis does not improve agreement much, doesn't improve agreement to give serious consideration. So the clocks, ideally, when they were moving eastward, they were supposed to gain time because they were supposed to be going with the rotation of the Earth, and then when they were going eastward, they were supposed to lose time because they were going against the rotation of the Earth. So what they found was when they were going west, they went out of sync, even out of okay. So there was 4 clocks right on each trip, and then all 4 of them were supposed to go in and out of sync corresponding to their direction. And what they found was only 2 of the clocks did that, and then they changed. Like it was varying on the clocks. It was completely random. So when they were going westward, 2 of the clocks gained time, and then the other 2 lost time when they were all supposed to gain. That kind of thing. So it was completely out of order. And then the westward trip, they weren't even within their expected range. Like they were way outside of it. So what they said here, or in this publication, they're like, yeah, it's not even close or whatever. And then in 1972, the next year, they re-released their what do they call it? I forget what the title of their other paper is called, but it's let's look it up real quick. Cool, spelled it wrong. Effeling Keating. Yeah, they call it the Around the World Sagnac Clock or something like that experiment. But anyway, they re-release it as if with corrections that they don't show how they corrected it, and they're like, okay, it was in alignment with relativity theory, even though during the experiment the clocks went out of sync, way outside of their error margin parameters 7 times, and they essentially kind of reset them. And apparently, this is a problem that just happens with atomic clocks that they don't even know why. They don't even know why it happens. So, so yeah, okay. So after all this experimentation and all this, they're realizing, okay, we have to correct for the velocity of the craft. That's what we have to do here. So through all these different engineering standards that are published for international telecommunications and all that, right? They say you have to sync the clock. And they call this a Sagnac correction. It's the way they portray it to everyone. They say they're correcting for the Sagnac effect. Or I'm sorry, they don't even say Sagnac effect. They call it a Sagnac correction, right? So let's see here. Sagnac
Quick question.
Go ahead.
Is that L? Is there a variable in there dependent upon altitude?
Yes. So all of these are synced. So they have their whole GPS system or whatever is synced to 20,000 kilometers or whatever. So they say at that altitude that there's the equal gravitational potential. Now, obviously, they're not at that altitude, right? But whatever altitude they're at, they have it baseline corrected for that altitude for a single baseline. Is that what you're talking about?
Yeah, because that would account for like the differential in the rotational speed at ground level versus wherever they're at. The Æther drift.
So let's see. Okay, so for your Sagnac corrections, now when you get into how do they define an inertial frame and stuff in GPS? Like, is a satellite, it's free falling around the Earth? What does that mean? Is it in an orbit? Is it free falling? So a free falling satellite is considered a local inertial frame. So it's an inertial frame. They consider it an inertial frame. Now in this free falling inertial state, this clock should not be able to detect its absolute velocity. It should not require a correction that corresponds to its absolute velocity if the Michelson-Morley experiment can't detect the absolute velocity of the Earth around the sun. So in the same respect, they say, okay, well, the Earth's falling around the geodesic and all that stuff. So the same situation is going to apply here. So we're going to see the actual corrections that they're making for these clocks, and they're not going to correct for any of these galactic or cosmic velocities that they say we're at. So when these satellites, whatever they are, right, whatever these crafts are, in their model, they say that they're in orbit around the sun. They're in orbit around the Earth. That's falling around the sun. These satellites are falling around the Earth. And when they're falling around the Earth, they're going to be parallel and perpendicular to the planes of motion for the cosmic microwave background, the center of the galaxy, and the sun. And when they're parallel and perpendicular to those planes of motion, their clocks should be out of sync corresponding to that velocity, and they never ever have to make any corrections that correspond to that. Right? These are first order velocity corrections that are being applied to the satellites based on its absolute velocity. So if we were moving at 5 different vectors through the cosmos and these satellites were falling around the Earth, they would absolutely have to account for these velocities if they were real. Yeah, dude, so they say, right? So they say, and they redefined physics, built everything off the back of this 100 years ago. Now we have applicable technology and all this stuff, right? And they're trying to figure out how to get it to work. And they're like, okay, what's how are we going to get this to work? Well, what they end up doing is they take that atomic clock, right? They sync it to a local they sync it to the rotation of the stars. They sync it to sidereal time. Then they have their whole network of clocks synchronized to sidereal time that makes no corrections based on velocity corresponding to any of the motions that are required for heliocentrism to be a real belief system, right? So, what's the implication here? That the Earth isn't moving and they have a coordinate system that's synced to the rotation of the sky. So here's a lot of people. I was going to say a lot of people have pointed this out through their careers in GPS. So basically, I came across this paper here, and what they were referencing was saying they were like, "Hey, we make all these corrections for the velocity of the craft and all this stuff, and supposed Earth rotation, but why don't we have to correct for the velocity of the Earth around the sun? It's 1,000 times greater than Earth rotation, and yet this velocity is never corrected for." And then we have let's see. So when we get dude, okay, so those corrections, they don't correct for those, but you know what they do correct for? When these atomic clocks cross meridians, right? So they can delete distance from them, but they don't need to correct for any of these things. So this is pointed out in by Ron Hatch in his book Escape from Einstein. After his 40 years of his 40-year career working in GPS and satellites and all that, he states that he's never once had to make any sort of orbital velocity correction in GPS. Right. And then we have here, so in regards to meridian corrections, for the time of propagation and for the atomic clock itself, this is in reference to an inertial navigation system, so a ring laser gyro. So that whole computer system will actually correct itself based on where it's at on the coordinate system. It'll change when you cross certain latitudes. So they have polar mode. When you cross the 86 latitude, it'll change coordinate systems. So they have a whole system designed on knowing exactly where things are on their coordinate system, and then the system outputs and tells you, where you think you're at on a coordinate system that you believe you live on. All right. So to kind of put all that into perspective with the corrections again, so this is in regards to some of the meridian corrections in the propagation rate for light. So it's been experimentally verified that the speed of light isn't the same going east that it is going west. So here we have an excerpt from Paul Marmot's paper where he's giving a what do you call it? An analogous rendition to an experiment that was done where they took a clock from Washington to Japan. So to kind of just make the graphic easier here, he does New York to San Francisco, but applies the same time scale reference. And he says, so let's see. So the global positioning system determines that after a clock moves from clock A to New York and towards clock B in San Francisco, its displacement accumulates an extra 14 nanoseconds approximately with respect to clock beta. And we know that due to Earth rotation, New York and San Francisco clock moves at velocity v minus epsilon, and with the velocity of rotation for v, and then the epsilon is the velocity of the truck. Therefore, 14 nanoseconds are subtracted to its display in order to give the correct time. So this is okay. So this is an excerpt from the paper that he's referencing to. So just to show you that this isn't just some stuff that he made up or whatever. Right. Okay. So now we have the whole system of how clock synchronization is kept. So they've come up with a way to divide 1 second into 192 millionths of a second. They've come up with a way to synchronize their network of clocks that are moving, and then for how they're moving, right? So on a plane, it would look something like this. It would follow the magnetic field, the magnetic flux lines. So this is kind of what we think is going on with the orbits or whatever. What they show you on the globe is that they're going around in an elliptical orbit like this, right? So the cool thing about transformations and reference frames and all that with relativity is that they say that due to motion being traveling along a curve, right, from another reference frame, your path of motion would look different, right? So if you pick another reference frame other than Earth and you look at the motion of satellites orbiting around Earth, their orbital path will change, and you'll be seeing their true orbital path, right? Because it'll be from a perspective outside of that reference frame, right? So you'll see its true geodesic path, right? So in its true geodesic path, you'll see that it's moving in a cycloid, so it'll be kind of just moving in like a circle that doesn't really complete. It just kind of goes in and out. And that motion is different from that elliptical orbit, where the acceleration and deceleration of that path will change, right? So the corrections aren't based on the true geodesic motion, right? The motion that would be covariant with all reference frames through the universe and all that with all. So they explicitly sync it to a stationary geocentric Earth time that's specifically in regards to the rotation of the stars for time.
Wow.
All right. Yeah.
That's so crazy.
So,
I mean, that's just so if anyone didn't catch that, essentially Einstein said that our orbital velocity has to be relatively linear. It's it's in our frame, it is purely linear as we experience it. But what Alan just showed is that there's actually a differential in the elliptical that they have to account for. So
yep, and they don't.
So
they explicitly don't.
And even that age-old, the age-old inkling that you get maybe when you first started questioning, our solar system model is well, even the elliptical of our orbit there's a banking motion there, right? Wouldn't we maybe feel that or be able to measure that? And as it turns out, the answer is explicitly, according to satellites, yes.
Yep. Yeah, so they account for a particular orbit, or I'm sorry, they account for a particular velocity, and they make no corrections outside of parameters that would indicate that there's another reference frame to be referenced to, right? So, all right, so that's how they keep time. That's what the atomic clocks are doing. That's their purpose. So they have a really precise way to break down a second. All right, so what do they do with that? So now we get into the second component of GPS. So they have the range measurement equation. So now we know how GPS keeps times in a local reference frame. They're going to use a range measurement equation in a specific coordinate system. One would say stationary, non-rotating. Now, when you look these up on the interwebs, you'll see that the ECI and the ECEF reference frame are one stationary, one's with respect to the stars, all this gobbledygook. Here's the TLDR. Kinematically, both of these frames are equivalent to being stationary. Doesn't matter if anyone wants to tell you if they're rotating or not. Secondly, they're both synced to the stars. They're both synced to the same time. So that GPS time that they established, that they set up for the ECI reference frame, everything is synced to that. Okay, so these measurements are going to be done in that frame, and then the ECEF reference frame is also synced to the same time. So with that, they should have a really accurate way to measure distance down to the millimeter, and then they should be able to take that distance and transform it to any map coordinate system that they have, and they'll have an accurate distance no matter what, because according to Lorentz symmetry, which is just mathematic covariance, right? According to mathematic covariance and the assumed speed of c, having a fixed speed, they should be able to take that distance and put it on any coordinate system based on the same time and have accurate distances for everything. Because the way that we'll get into how the range measurement equation works, but the reason here, the big distinction here is that GPS doesn't derive distance the way that that people would that you would typically think of it as doing. So we'll get into that now. So GPS uses what's called a range measurement equation. So it looks like this. This looks crazy. What does all this mean? So this is the absolute value of the time that the signal was sent and received, multiplied by the time by c, and that gives you the difference, which gives you the distance. So the distance in propagation from when the signal was sent and received gives you the distance. So that's how they derive distance. So the traditional method of deriving distance would be having a unit of measurement, and then mapping it out and going, okay, so let's say one of these cubes is 1 unit of measurement. So you would go 1 unit of measurement, 2 unit of measurement, 3, 4, 5 units of measurement. So you would say the distance between C2 and G6 is 7 units of measurement or whatever, right? So that's not how GPS works. GPS says, okay, I'm sending a signal and my location is right here, and it took XYZ all the way down to the billionths of a fraction of a second to get it, or that's when they send it, that's encoded with it, and then your receiver gets it and it starts making references off of that, right? So that's how distance is derived within their coordinate system. So it's different from the traditional method, right? So we'll get into a little overview provided by Wang on how c is used in relation to this equation. So some people think that the range measurement equation is based on the constancy of the speed of light. On the surface of it, this may appear to be true. So again, this equation, there's your boy, speed of light. Look at him, he looks pretty constant. This equation looks like it definitely depends on this being a constant. So let's see. So on the surface of it, this appears to be true. C, the speed of light, is the only velocity term that appears in this equation. Expressions such as c plus v and c minus v, which are often seen in discussions of special relativity and classical physics, do not exist in this equation. Therefore, some people would conclude that this equation is correct. Special relativity, if correct, this equation has been proved to a high degree of accuracy. Special relativity has been proven with a high degree of accuracy, blah, 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 to 5 times 10 to the minus 9, right? So they're saying that if you look at this equation, you're like, okay, like bet, special relativity, okay? Speed of light's super constant. But if we try not to judge things on their appearance, but we should try not to judge things on their appearance and try to grasp their essence. If we analyze the implication of the range measurement equation carefully, we will find that contrary to what appearance tells us, that some people think of the correctness of GPS's range measurement equation, it actually leads to the incorrectness of the principle of the constancy of the speed of light, and furthermore, the principle of relativity. This may seem unexpected, but it is quite understandable if we compare it with sonar systems. Recall that in underwater navigation, sonar uses the same range measurement equation in a reference frame based on water to calculate the distance traveled by sound, even though the sound receiver is moving relative to the water. The difference there is that the speed of sound in the reference frame what they're using for the speed of sound is used instead of the speed of light in a vacuum, which is c. However, no one would emphasize the constancy of the speed of sound, and contrarily, everyone thinks the speed of sound is dependent on the motion of the sound receiver. So pretty big implications there for the equation, because on the surface of it, it looks like, that there's nothing weird going on here. But what they're going to find out is that the distance derived is based on a variance in C. It's going to show a variance, like how they're measuring distance. It's going to be based off of a variance in C, because that's the only velocity term provided in the equation, right? And they're using the time of propagation to derive distance. So the only thing that's going to vary is going to be the thing that's producing the velocity term in the equation, right? Everything check out so far?
I mean, you're giving me cog dis.
All right.
How can this be?
It's a real mind bender or whatever. So we have here the successful operations of GPS is based off of the range measurement equation when used in a specific reference frame. So keep in mind too, this is GPS's accuracy depends on this equation when used in a specific reference frame. So the ECI shows the correction. Blah, 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 okay, and then the Sagnac effect is fully interpreted by this equation as well. Get into some of that here in a second. So what Wang's proposing here in his paper, he points out the like how this equation works and how it accounts for the Sagnac effect. So they say, oh, the Earth's rotating, but that must mean that when the signal was sent here, that because the Earth's in rotation, that now they're slightly out of position due to the being physically moved out of position, right? So what Wang is saying here is that and they have to apply a correction on the back end to account for this, and they call this a Sagnac correction. Right, but what Wang's pointing out here is when you use this equation and you apply it to a scenario, you get a result that contradicts relativity. So I'll walk you through the scenario here. So we have a stationary satellite and a moving satellite, doesn't matter either one, and they send a signal out at the moment when a stationary receiver and a moving receiver intersect each other. So when these two gentlemen are at the same distance apart from each other, there's a signal that's sent, and it's going to receive at the same time of their intersection. And what they find when you run the math and GPS and all that, you're going to find that the relativity says these two should get the same. They should receive their signal at the same time, and the distance derived should be the same, right? But what actually happens is R2 receives his delay he receives his signal at a delay proportional to his velocity. So that's completely contrary to special relativity. And what they show, the only velocity term in this equation could be the speed of light, right? So the speed of light varies proportional to the velocity of the receiver, and that is what makes GPS so accurate. They reference that. They use the time difference in their time system to calculate that, and it shows that there's a variance in C. So when you go to the ICD documents, you'll find that the assertions made by Wang in his GPS papers are fully substantiated. So we have here the Doppler shift of frequency of the received carrier signal is proportional to the velocity of the receiver with respect to the satellite along the line of sight from the receiver to the satellite. So they say because obviously they're not going to say, hey, in this manual the speed of light changes. They attribute it to just a Doppler frequency shift within a constancy of the speed of light, but they're forgetting they're also deriving distances based off of a time interval. Don't we got to
go back to page 1 of Albert Einstein's 1905 paper at this point, right? Like even that alone, even invoking the Doppler shift there, that requires an absolutely stationary space
to maintain C, to even proportion it against the velocity.
Yeah.
I mean, it doesn't, invoking a Doppler shift, automatically presume that there is a medium through which the light is traveling.
How dare you? Number one, and number two, how double dog dare you? It's definitely not an Æther that's causing the proportional variance. But yeah, no, that's absolutely, and that's actually that's one of the big points that I honed in on my general relativity presentation, because they attribute all these compression mechanisms and stuff and all these Doppler effects in space, and it's like, how are you justifying the energy exchange to produce a frequency shift, bro? And they're just like, oh, space-time's compacting. It's like, all right, dude. But anyway, so they say here they admit to the Doppler frequency shift, and then they just say that's just like they just work it off of the back end of that, and they say that it's all good off of that, and they use that to derive the velocity and apply a correction to it based off of that frequency shift. But that's not even what happens at all. It derives the accurate distance in the first measurement down to the millimeter. Um, so, not this isn't even this is just something that they are trying to present to explain the fact that the speed of light changes.
Dude,
To
I
produce
think
these
Navstar. I think the Navstar document just doesn't get it. They just don't get relativity, and they don't get how the satellites work.
They don't get it. And then to
They get it, but they
show,
don't.
so to kind of show what all this means, like what's the ECI? What does all this mathematics and clock synchronization mean? What does it mean to be in reference to the center of the ECI and all this shit? So when you go to Wikipedia and you see GPS and all that, you see their orbits. So you see this GIF over here. They kind of say that you, from any given point, you have like, what is it, 6 or 12 satellites or something like that. Can GPS satellites have access to you? So to kind of give a reference to that, what they have is they have a network of crafts that are going in a circle, right? And they're referencing their location and speed in reference to the center of the ECI. So if we take a Gleason's flat map, just call this the ECI, and then we have our clocks at altitude above us, or our satellites right above us carrying clocks and satellite equipment, GPS equipment and all that, right? So they're referencing their time and distance and location relative to the center of this frame, right? So they got a red line to describe that propagation and reference, right? And then we have an observer here who's number 6. So he's making a GPS request. He's saying, "Hey, where am I at? I'm trying to figure out where I'm at." So these satellites send signals to him, and they encode their references to where they're at in reference to this coordinate system, right? And then this guy's handheld system is able to, with this information, is able to figure out where he's at in reference to the center of the ECI. And then they just do a transformation to the ECF coordinate system, apply a correction to it, and then that tells this person where he's at on the globe. Right? So the way that the satellites work is that they're already sending out signals with their with the information cooked into it to be proportional to what they need to fit the globular coordinate system. Because if you recall back to what Paul Marmot pointed out, let's see, he points out that they make meridian corrections for the time of propagation and for the atomic clocks as they're moving. So anytime there's what you would call like the equivalent time for C to propagate across meridians, they just delete that time. So when using GPS to get your location on the globe, you have no idea. It's only going to be local to you and like tell you like where you're at specifically
On a globe.
on the globe. Like it's not gonna like you're gonna like if you because there's people that do this thing where they'll be like, oh, we verified our measurements with reciprocal GPS zeniths. Like, dude, like they for real use GPS zeniths, dude. So that's exactly going like that kind of stuff is exactly what's going to output the globular coordinate system. When you hit up a distance propagation of that long, right? The meridian corrections cooked into it, it's going to give it's going to always return back to the globe. So that's kind of what I wanted to illustrate here with all this math and how it would work on a flat earth and stuff. So it's just you would have your system propagating, or you would have your network of satellites doing their thing, whether it's electrostatic tethering and they're going around the equator, or their balloon network, doesn't matter, whatever, right? How they're referencing and what the and how it works. This is it right here. This is all they did. And they just sync this stationary frame to the stars, and then they have their ECI or their ECEF frame, so that when they apply. So this is the other crazy part, boys. So remember how I said that the time for the ECI and the ECEF frame are the same? So they derive this distance measurement. Now, when they apply that distance, it should be the same under all frames, but it's not. When they transform it, it's not the same. They have to make corrections to it, but they're the same time.
Those are Sagnac corrections, right?
Yeah. So these are corrections that they're making on the back end to fit everything to their coordinate system. So this is exactly how the entire system works and tells you where you're at on the globe, because on the back end they make a first order velocity correction to the time of flight. Like, that's insane. It's not supposed to be like that. They wouldn't have to do that.
And don't forget to mention, bringing it back to the beginning, that it's measured physically, because the cesium's getting cooked at a different speed in a certain direction, because it's literally propagating in that little atomic clock the EMF faster in one direction.
Yep, there's direct explanational math to explain everything that's happening, and that's exactly what Alan is showing here. And yeah, essentially, you would know if anytime you're invoking GPS, you can never know that they would possibly be doing anything other than this. This is such an awesome diagram because, really, unless you've gone out and done physical measurements against something other than the sky, because that's all they can invoke is the sky, which most of this is built on, but until you've gone out and done measurements against something other than the sky, you cannot possibly assert anything other than, you have to acknowledge the fact that all of your coordinates, all of your mapping is based on what's been given to you, which is based upon a model that is, you're every time you're receiving any GPS information, it's coming through this filter. There's a transform happening. It's giving you a coordinate relative to the ball, not a coordinate relative to, your absolute space on what, a potential flat Earth map would actually look like.
100%, man. And the fact that they apply these corrections at all is a violation of special relativity. It shows directly that the speed of light isn't the same. And I'm not even like, this isn't something that I'm like, I'm not like, I didn't just discover this, right? Like, this is stuff that people already know about in the field, academics, etc. Like, there's published papers on it. It's just no one talks about it. And then everyone just acts like, no, that's
Well, if
not
you
the
come
truth.
out and say it too directly, like Paul Marmot did, then, and even he was still trying to be polite about it. But if you,
Dude, he was still polite about it, and he even tried to co-opt the quote-unquote relativistic effects and keep the whole paradigm intact in terms of relative motion and all that gobbledygook, and they still slayed him. And I think personally, it was because he mentioned those meridian corrections and that stuff. Because that's devastating, dude. The fact that they do that, because that's like when we first were going over how GPS works and the variance and all that. Shane was like, "Oh, okay, so like there could be a shadow coordinate system." Like, he realized immediately the implication of it, and then but there was like no way to like back that up. The meridian, like, that's it. The meridian corrections are it. that's like that's a fake court. Like, you could never reference that to anything. Like, so if you're questioning GPS, right? Like, that's it.
yeah, and who
Or,
was it? Who was the people, the scholars that they got the GPS data to do analysis on it, and they found when they received it that it had already been transformed, so they didn't even actually get the raw data, right? It was transformed GPS data that had already had Sagnac corrections applied and had essentially all the coordinate system baked into it.
Yeah, that was the boys Wolf and Pettit right here, 1995. They analyzed some quote unquote raw data from a GPS center in Chicago, where they were analyzing raw data trying to determine the one-way speed of light. Because with this clock reference system being so precise, and the measurements depending on a one-way it's a one-way measurement. So they're like, oh, okay, we can measure the one-way speed of light. So what they, that's what they were trying to do, and what they found is that the data on the back end that's saved in their storage, units or whatever, is already Sagnac corrected, so you can never tell any distances or variance in the speed of light from it. And their determination was that the speed of light is the same in all directions based on the data they observed. But they noted in the paper here that the data was already Sagnac corrected. So it's like, well, they didn't determine anything. They looked at something that was already fit their presupposition and then said, "Yep, all nothing to see here, folks." That's
Question.
crazy. What's up?
Thinking about the meridian corrections, I mean, we know that they're doing the corrections on the server side on the back end before it gets spit out to your phones. But because they're doing these meridian corrections, like if you think about time zones, right? Time zones do not match meridians. I mean, if you looked at like the time zone thing, so like if a person was to take the already converted coordinate system that we get to our phone and they wanted to try to like work it backwards, they wouldn't be able to because they wouldn't know what kind of like they wouldn't know the actual transformation that's happening at each meridian line. Like that information is not actually described here, I don't think. You would have to know that in
No,
order
you
to be
no,
able to
you
work it backwards.
that's exactly it. You would never know. And then so when they're like, "Oh, the GPS I decoded the information and it said that it was at this altitude." Well, all that's already going to be cooked into it because this is going to be a scaled invariant system. So it's gonna be obviously a local system, and then it's gonna be scaled out to where they can just have, okay, all the GPSs are at 20,000 kilometers altitude, blah blah blah, right? And they just start cooking in everything under that paradigm, and it's not even at that altitude. You know what I'm saying? But yeah, like, you're exactly right. It's gonna show exactly what it needs to show for the globularists to continue their belief system, even though the corrections made to the clocks themselves contradict their theory, show the Earth stationary, show they only account for one rotation. It's the rotation of the stars. Why is the rotation of the stars being calculated in reference to something that's falling around the Earth? Doesn't make any sense. It's insane. Like the implications here are so solid that if you just take us like if like the only I don't know, it's wild, but
Real quick, Alan. I think
Mhm. like the only
the
like
atomic clock thing, it's totally part of the same issue, but it's actually a separate point if you really break it down because like for one, the signals themselves that are getting sent from the satellite to the ground are propagating at different speeds, right? But also the freaking atomic clock internally, the EMF inside of it is propagating at a different speed. The little C field where they shoot the RF into the cesium, right? Like it's literally traveling. It's on a nanoscale because it's a tiny little machine, but like on a tiny scale, it's traveling at a different rate in one direction versus the other, and it's causing so many billionths, so many 8 billionths of a second to be off. Like that's they're physically validating the fact that there's a difference because those atomic clocks are synced up, and we know that they're like perfectly synced at rest, and nothing causes them to get out of sync at rest. And if you think about them things moving through the sky, there shouldn't be any difference in the local time of the clock, right? Even if they're, moving through the air and they're getting there, you know, and you're accounting for motion, all these things internally within the clocks themselves, they should still be synced. So the fact that they become off shows that there's like some super viscous material that's affecting the flow of the RF field that's cooking the cesium, which would be the ether.
How dare you
are you
again?
are you trying to tell me that there's a kinematic viscosity of the ether, bro?
I mean, something's slowing down that RF field, bro, to make it cook slower.
How dare you? Yeah, that's exactly it, man. And they just don't talk about it, bro. Like they have this guy, right? So while they're trial and erroring these experiments and figuring out how to get the how to build the GPS network to work correctly, right? They have your boy Allen Weiss and Ashby, and then they have this guy Ashby specifically from this experiment go on a 20-year tour telling everybody, guys, we did a GPS experiment and we found that we have to account for the Earth's rotation to keep everything accurate. And that's it's like when you go to Google and type in atomic or GPS, Sagnac or anything like that, like the first stuff you'll get is all in reference to Ashby. You get Ashby out of your mind, and it's like, bro, the distance derived isn't invariant under transformation when both times are the same in the ECI frame and the ECEF frame. It's not a rotation issue. You guys are just playing around.
Oh, so you're saying when you sync up the times, when you get the time synced up between the two reference frames, it changes the distances? Well, it would
No,
have to.
No. So the distance should be the same
Wait.
under all, because the time is the same in their paradigm, because the time is the same and the speed of light is fixed. Any distance they derive in the ECI frame should transform invariantly to any reference frame.
It
I mean, yeah,
should, yeah, because there's only three variables.
any coordinate system. No, not should. It, like it has to. Any distance they like it's part of their it's part of covariance invariantly, but it doesn't. They have to correct
Right.
it.
That's my point. It
So
doesn't. Yeah, I'm saying in actuality.
oh, I'm sorry. I thought you said it backwards. No, no. So when they transform it, right, in the new reference frame, where they're using C as a fixed value, there's a discrepancy. It's like, how do they fix that? Oh, they SAGNet correct it. So they have all these guys telling everyone that they're SAGNet correcting, and that's all it took. Like this guy's a big part of it. A big part of, and then like, yeah, I don't think he's like in on it or like whatever, obviously he's like, oh yeah, SAGNet correct. And then they were like, hey, go on tour and tell everyone that for 20 years. And he was like, okay, bet. I'm sure he's not a bad person, but like he's responsible for the narrative of these corrections, and they directly contradict relativity theory. So they
want
make
to hit a home run with this, bro?
Send it.
You look up, and it might be harder to get a hold of these documents, but I know you're really good at finding them. ICBMs. I know that ICBMs, you're talking about the center of an ECI reference frame, right? And how they globularize it. But if you look at ICBMs, they readily admit that they track off Polaris. So like if you were to get a hold of some papers that show the math for that, it wouldn't claim that it uses, and they use similar technology, but it wouldn't be claiming some center of an ECI frame. It would be directly claiming Polaris. So if you're saying the center of the AE, the azimuthal equidistant map, right? The center of that, you were equating that to the center of an ECI frame because you're saying they're doing like an AE conversion, but Polaris is the center of an AE map. The ICBMs already admit that they track off Polaris. So if you're able to get a hold of the math and compare it, and it shows
dude, that okay, yeah. So so why would they change it? Why are they saying they're using a different reference frame than the ECI then, though? Like what
exactly.
Do you know what their story is? That's interesting.
I don't know. I don't know what it is as far as the math goes, but I know that basically it's supposed to be because the ICBMs are supposed to be self-sufficient, like totally enclosed system that's not dependent on anything else. So once they're launched, they're totally self-reliant. They just track off of their initial launch position, their current position, Polaris, and the projected target. So they track off the stars, bro.
Yeah, okay. I'll have to look into that. That would be really interesting because like the equivalence would be there with that coordinate system. And then they're just saying Polaris to make it seem starular, right? But it's just the same thing that they're doing already. That would be
if they end up doing the same Sagnac correction though, and everything checks out the same with what the math they're doing is, it would be pretty damning because it would show that Polaris is the center of the ECI frame.
Yeah. Yeah, it definitely will. All right, so that's see, we're almost done with GPS here. So let's round out here. So this is how they kind of say it works. So my rendition was my rendition of the ECI on a azimuthal equidistant projection map is as follows. And then how they say it works on the glob is they're referencing the center of the glob, and the satellites would be out here, and they're triangulating distance relative to the the surface of the glob from the center from their signals, right? So very cool. All right, so to end out here, so the principle of relative simultaneity is not accounted for in GPS. So to one of the big consequences of the speed of light being the same is the principle of relative simultaneity, meaning that for certain observers that are in relative motion to one another, there isn't a cohesive chain of events that can be followed because it's all relative, right? And the speed of light's constant. So they're going to see events happen at different times, and it's not all going to be the same, right? So this is going to have to be accounted for in GPS because everything is synced to GPS time, right? It's all synced to the same cohesive timeline. So there should definitely be principle of relativity corrections, right? Because this is like the main crux of the belief system. So C is a fundamental postulate of the theory of special relativity. As a consequence of this postulate, observers moving relative to each other will not perceive events occurring simultaneously. Upon this phenomenon, this phenomenon is called relative simultaneity. The lack of the universal timeline of events is a direct consequence of the invariance of C, which mandates that measurements made in time interval and spatial distances will differ between observers in relative motion. All right, cool. So the GPS is definitely going to have to correct for that, right? Because like even all this other stuff that violates relativity, at least has to be something to make this cohesive timeline work, right? Let's see what Wang has to say in his paper. Global simultaneity versus relative simultaneity. Oh, what's global simultaneity, you ask? Global simultaneity is a special case of simultaneity that happens locally to the Earth that excludes all relative simultaneity effects, and those effects only occur outside of the Earth reference frame. So if you want your relative simultaneity, you'll have to check another castle. So in any debate about in any debate about the speed of light for the problem of simultaneity is always a focus. Special relativity claims that the relativity of simultaneity, which states that two events occurring at two different places, which are viewed as simultaneous for an observer in a system, usually are not simultaneous if observed for an observer in another system. But contrary to this, simultaneity is key to the process of GPS. GPS is a timing ranging system. It does not directly measure the distance between two places where events uh, the distance between two places where two events, i.e., signal transmitting and signal receiving, occur. The the measured that it measures the difference of the difference of the two instances where when the two events happen and when the distance is calculated using the range measurement equation. GPS, especially in its space segment and control segment, make a huge effort to maintain GPS time, or simply GPS time, or GPS system time. Sorry. In a scope where GPS is applied, roughly a scope of a diameter of 50,000 kilometers or bigger, if one is using GPS, one is using GPS time, and therefore the concept of GPS of simultaneity of GPS. So if two events happen at two different places and the coordinate system is given for event number one, so x sub one, and then the coordinate system for event number two, x sub two, are simultaneous if the time in event number one is equal to the time in event number two. So this is true no matter who the observer or the receiver is, or where the receiver is, what its status is, or what speed it is. This is the basic operational principle of GPS. We call it global simultaneity. In the textbooks about special relativity, the most commonly cited example about relativity of simultaneity is the example of the railway platform in a moving train. It says that two events, e.g., two strokes of lightning, A and B, which are simultaneous with reference to the platform, are not simultaneous with respect to the moving train and vice versa. But now GPS receivers have been utilized extensively on railway platforms and moving trains and lightning at two different places, A and B conceptually at the same time, as the emission of GPS signals from two satellites or two DGPS stations. In fact, if the signals are emitted from two satellites or two DGPS stations at the same GPS time, both GPS receiver on the railway and the GPS receiver on the moving train would acknowledge the two events of the emission of the signal to be simultaneous. Without this basic acknowledgement, the GPS receivers cannot function at all. So, what do you know? They can all accurately register and derive distance based on the same cohesive timeline.
Wow.
And they all get their information at a variance relative to their velocity. Thanks, Æther. Crazy.
Oof.
So this is a huge problem because the distances derived here in these scenarios, where two signals are sent to observers that are moving and stationary, shouldn't derive the same distances. But they don't need to make any corrections. The range measurement equation accurately derives the distance down to the millimeter, with no built-in corrections. It just does it inherently. by ratioing time against the speed of light.
And yeah, I mean, I was talking about the twin paradox earlier and how it's nonsensical. And Alan just spent the last hour explicitly demonstrating how it's nonsensical. I mean, this entire concept, it's, I've said it a bunch of times, but I'll say it again. It's hilarious because when you first start looking into all this stuff, you start getting gaslit by people saying, oh, well, this proves special relativity. Oh, no, this proves general relativity, and you start to feel like, oh, okay, I guess I don't really know what I'm talking about. Maybe these people are right. And then you start looking at it, look closer, right? Because one of the things I was told a lot was that GPS, the atomic clocks, they proved special relativity and time dilation. That's what I was told, and I listened to some crazy arguments, and I felt stupid. And then, Alan started doing these presentations and talking about this. I got a hold of Ron Hatch's Escape from Einstein, and it's just been getting exposed more and more ever since then. And lo and behold, it's exactly the opposite. Like, it's actually really awesome because it's one of those things, like all of this, where once you really, really start looking under the hood, the more time you spend looking at it and picking apart what they're actually doing, the more it all actually makes just mechanical sense. Like a classical framework explains it all. The velocity is proportional to the ether wind. The decay rate of the atomic clocks is proportional to the ether wind. C is not some magical constant that space and time bend around. There's no such thing as time dilation. It's just a sensible, it's so sensible. It's like, it's so amazingly sensible that it allows us to have precise measurements of where people are with their devices.
Dude. With no crazy corrections or transformations. I mean, dude, if relativity were true, there would be a never-ending cascade of principle of relative simultaneity corrections, dog. It would be ridiculous.
It would be insane. Yep. I mean, it's just all they can do is, hide what they're really doing in an ECI frame so they can call it a transformation.
Yeah, that's a big part of the deception, right? Is that transformation out of that frame. And even doing that in and of itself violates, reveals the covariance violation, which, as it turns out, no relativist actually cares about. Like, dude. I thought for sure learning about dude, I thought for sure learning about covariance, I could start pointing this stuff out, and some of the relativists would be like, "Oh, no way, that's crazy. I need to now abandon my belief system." No, that's not at all how it works. They immediately become pure relativist and don't give covariance goes right out the window. So don't ever be fooled by someone telling you, "Oh, these equations reduce back to Newton's equation." Dude, if they reduce back to a pile of dog shit, they would be content with that and happy. Like, they don't care about covariance. That's all an illusion. As soon as you start showing them covariance violations, they don't care.
Yeah, they'll either gaslight you and pretend like you don't know, even though they don't know, or because they just actually don't know. A lot of them just really, really haven't looked at it close enough to figure out what's being measured in the lab frame, aka reality. Or they've fought through it, and then they were faced with the decision. Do I abandon this belief system, or do I drop my do I take the leap of faith to continue this belief system? Because there's a leap of faith required at that point. And I think most of these people, when you get to that point, it's kind of a brilliant system, right? Because most people don't get to that point, or at least historically, it seems like a lot of us had not gotten to that point. But when you get to that point, those people, they're already deep in school. They've got debt, funneled into this. They're trying to get some kind of, research funding, or they're trying to stay in the, in all the cool crews, be able to get invited to these science conferences, or, be invited back on other science YouTube channels, not be castigated as a crazy anti-Einstein or flat earther or whatever. Like, they're already in too deep. They don't have the option to say, "Oh, yeah, this is a religion. I'm done." It's like, "No, I've already wrapped my entire identity around, believing all this crap." So, I've got no choice at this point. It's not worth it for me to drop my ego and drop all my pride and drop all this stuff I've built my life around. So, you know what? Screw it. I'll just, I'll swallow. I'll just take it as it is. Pure relativism. Everything's purely relativistic. Everything's post hoc, ad hoc postdictions. I can't. My math isn't even predictive. I can't even make predictions about the reality that I live in. But it is what it is. We know it's real because we just know it's real.
Dude, you can only make predictions that are indistinguishable from classic mechanics. Like how crazy is that, bro? The Pound
Dude,
Repka experiment
perfectly
and
said.
Pound Snyder experiment, like I don't even know how they got to the experimental phase and didn't realize that the predictions for both theories were the same.
In another one where
And
it was like, yeah, they say it's proof of relativity, and then you start looking at it and looking into it more and more, and it's like, oh, no, this actually is a lot worse than you guys think. Because then you get
Dude,
into the
it's
Eddington experiment.
oh, dude, the Eddington is nuts, man. They gaslit the entire world by telling them that light bends around the sun, dude.
So yeah,
People quote that to this day as proof.
like Pound Rebka is not coherent with the Eddington experiment. It's two different frameworks essentially, unless you just accept again classical mechanics to an extent. Although I don't
Dude,
even
dude,
like.
e-
Yeah, go ahead.
I was gonna say even the Eddington experiment contradicts relativity, bro. What they observed wasn't even at a distance that falls under the Einsteinian prediction. Like the whole thing is crazy.
And for those
So
that don't know, Pound Rebka was when they first discovered that electromagnetic waves, which all the time, by the way, when we're talking about light waves in all these experiments and such, sometimes we'll talk about radio waves, sometimes we'll talk about light waves. If anyone's unclear, it's all electromagnetic waves. And in that paper that I brought up earlier, 1905, on the electrodynamics of moving bodies, Einstein makes it really clear that we're talking about all electromagnetic waves, which includes radio waves, microwaves, light waves, visible light waves. So in any case, where was I going with that?
the Pound
Pound
Repka
Repka.
showed a
Pound Repka.
contradiction.
So yeah, they shot electromagnetic waves downwards from the top of the school, right? And
Yep.
then they were able to detect an exact relational propagation rate that came out to be the exact downward acceleration that we experience as quote unquote gravity. So light was getting pulled down and moving faster than c, quote unquote, faster than the quote unquote speed of light, shooting down from a building, which you got to think that also implies that effect is being, that effect is occurring with, would be in that case, would be occurring with sunlight, moonlight, starlight, all the stellar, phenomena. So you have to take that into account when you start, when they want to start talking about C being constant, and they want to talk about their model, they've got to make sure that their model's coherent. And that's where, the Eddington experiment comes into play with all this too. So how do they even, the coherence of Pound Rebka? Were you going to say something about that, Alan?
Yeah, I was gonna say it's really interesting, right? So, Michelson Morley, they're like, oh, there's no Newtonian force to be measured or whatever because it's the curvature of space time, right? But here they tried to measure the curvature of space time. I'm sorry, the effects of the gravitational field of Earth or whatever and its relationship with space time curvature. They tried to measure that, and they got a fall rate, or they got a frequency shift in which would correspond to the speed changing, right? Which corresponds to Newtonian gravity, showing that there's a force, moving the light down at a faster speed so that it's gaining speed. And that prediction is also the same as the relativistic prediction in terms of the frequency shift, but the classical theory predicts the same frequency shift, but also that the speed changes. So to determine that specifically, they would need to do the experiment again with an atomic clock. But it's like, dude, they threw the one thing out and then claimed that the same effect is causing, like, it's so backwards, dude. The same effect is causing the frequency shift that can't be measured in the other experiment. Hello. Like, dude, what? It's so crazy. Like, they
Yeah.
have no paradigm in which they could explain how gravity's interaction with light. Can't. Because if they try and do it through the lens of measuring relative motion of Earth, can't be done. Right? But when it's falling down, they're like, oh, it could be done, but like maybe we'll do it again with an atomic clock. Guys, they never did it again with an atomic clock.
Spoiler alert.
This experiment that's touted as proof of relativity, even though it's indistinguishable from the classic mechanics effects, they're like, yeah, we should do it again with an atomic clock. They never did it again.
I think it's important to note that the whole entire point of relativity math even existing in the first place is because it is supposed to be there to describe accurately phenomenon that cannot be explained by classical mechanics. Because if something is sufficiently explained by classical mechanics, you obviously already can see like the dynamic causation of those effects because they're classical effects. So if there's an equivalency between a classical description of something and a relativistic description of something, that automatically shows that the relativistic description of it is just a post hoc, conversion of a classical effect. They should
Yeah,
not be the same.
Yeah. What you'll find too is often that the relativistic effect, like in the frequency of light, will be like such a small, minuscule effect that it's just like how are you gonna? So like the rest of this frequency shift is part of like this thing you described classically, but this like really tiny sliver in the frequency on a scale that nobody could possibly even figure out. Like this is the relativistic. This is where the time dilated. like what? It's like how could you possibly distinguish that from anything, right? It's insane.
Unless it's a 100-meter coaxial cable and with photonic crystals at the front that you're shooting light through, then it's got like a 70-meter lethal attraction it goes under.
Oh yeah. Well, in that case, like that would be pretty damning if that didn't contract properly, right?
That old Earth rotation does some crazy stuff, huh?
Yeah. Dude, I hear
But
it
that
rotates
also
in the
been
opposite direction in the south.
dude, dude, the fact that the downward bias causes light to propagate faster
Well,
proves
hold
that
on. Hold on.
gravity is electromagnetic in nature, bro. I mean,
I mean, bruh.
How dare you again?
If only there was some
You're
sort
pretty
of
daring.
set of equations that had an electromagnetic equivalence to what they call gravity or whatever, right? So if only somebody went through that. Where's my boy Mince at, or Mice, or whatever his name is? Mince Mice,
something like that. Yeah.
Mice guy. Yeah. Anyway, pretty crazy stuff, man. So yeah, so the quick recap here. So GPS had been out for a while, and then in 1995, all the engineers were starting to write and publish stuff and ask questions, and they were like, "What's going on with all these relativistic corrections that we're not making that are supposed to be proof of relativity in this technology that we're utilizing?" So an official statement was kind of put out by your boy Henry Fiegel and Raymond from the Joint GPS, or the GPS Joint Program Office, right? They say, "Hey guys, stop asking about the relativistic corrections. All you need to know is that the equipment that we're using is sensitive enough to only really account for the classical effects. General and special relativity essentially cancel each other out. Stand by. We'll correct relativity in future iterations of GPS technology." And then it just kind of goes over here and explains why velocity and gravitational corrections aren't aren't included yet because they cancel each other out to close enough to where it doesn't really matter with the sensitivity of the system that they're using. And this guy, Carol Alley, from another atomic clock experiment where they were able to get the atomic clocks to stay in sync for 14 hours using Einstein synchronization before they, disastrously failed. And then all of the standards put forward after that were to sync them to the Sagnac effect. So shout out to Carol. But anyway, he writes in and says, and that if one perhaps does the explicit recognition of the special relativistic effects, I mean, it took a long time to get the general relativity down properly, and I think that it's more or less correct now. But it's the absence of any explicit acknowledgement of special relativistic effects due to the speed of light being the same whenever measured by an observer, leading to the relativity of simultaneity and the associated Lorentz transformations in physics. There's nothing of that modeled at all in the current system, and I think it should be. Thank you. What a polite man to say, hey, this mathematic framework of how we interpret light and how I think GPS works, even though it clearly works off of a different system, I have this whole framework here, and I think we should use it. Thank you. The relativity of simultaneity and the associated Lorentz transformations of physics. So if the speed of light is the same in all reference frames, it's going to lead to relativity of simultaneity, so no coherent chain of events for observers in relative motion to one another, right? And the associate to therefore go on mathematically describing the world with this framework, you then have to use the associated Lorentz transformations to describe that. And he's saying there's nothing of that at all modeled in the current system. And I think it should be.
Just like, hey guys, I do a lot of work with this. I put a lot of time into this. It's kind of like embarrassing or hard to explain to people that are asking me a lot of questions. And I don't have answers for them. Like, you think maybe we could just make something up to make this make sense? Like, please, thank you.
Yep. So, and to be fair, they did tell you, boys, stand by. We'll come through with some corrections. And in later iterations of GPS, so they now account for general relativity. They say that at the altitude that the GPS satellites are at, they account for an equal gravitational potential at that altitude. You know what else is an equal potential? The electric current that emanates from the ground that goes to the sky. So as that field strength increases at altitude, the impedance caused by that field is going to, increase. So there's an equivalence there for what they're accounting for. They're calling it a gravitational potential, right? So they're saying that Earth's gravitational field, right, at 20,000 kilometers away from Earth is an equal potential gradient, right? And they are just accounting for an effect at that altitude. So they're making a clock correction. They're making a clock retardation correction based off of that. And then they say, okay, we're going to get into our special relativity corrections now. So we have to account for the Earth rotating underneath the satellite, right? For some reason, in the clock correction, right? And then we have to account for the velocity of the craft through the, in addition to the velocity of the rotation for some reason, right? So they got their velocity corrections for general and special relativity, and these are baby corrections, right? And then they have their Sagnac correction, which is an entirely separate correction that they apply through what's called a Lorentz rotation, separate from the Lorentz boost, which is the type of Lorentz transformation that we're all familiar with, where we go, oh, okay, length contraction, time dilation, where they're changing those two coordinate systems by shortening the distance, right? So in a Lorentz rotation, they're actually inverting those axes of the x-axis and the time axis. So typically, the time axis is perpendicular to the x-axis. So what they're doing is they're inverting that so that the x-axis is perpendicular to the time axis.
So you just never know. You never know which axis you're going to need.
Dude, you don't know if it's the axis of rotation, the
Literally,
Lorentz
that's
axis,
just
a
the way
fucking.
nature is, man. That's just the way nature is. You just never know which axis you're gonna need. Sometimes you might need one, sometimes you might need the other. Sometimes you gotta rotate it. It just depends what nature's in the mood for.
You never know when you're going to have to assume a geometrically convenient position to view something that violates your worldview. So to always have like a cylinder queued up to be in the center of, like, smart.
You either use
Uh,
two Lorentz transformations, or aka two Lorentz boosts, or
Yeah.
you use the Lorentz transformation and a Lorentz rotation.
No, yeah, we just one rotation is equivalent to two Lorentz boosters.
Oh, okay. So you don't have to actually do a transformation with the rotation.
The rotation itself is the transformation.
Ah, okay. Gotcha. So yeah,
Alan,
pick your poison: a couple boosts or a rotation of your entire coordinate system.
Yeah. So
real
let's
quick
see.
for you before you
Mhm.
close, there was somebody in here earlier who was asking me about the Sanyat corrections and stuff, and they were saying, are you sure they're not just correcting for the velocity of the craft? I'm like, well, they of the GPS satellite. I'm like, well, they are, but they're also accounting for like this drift effect. But just to be clear, like step one, right? Accounting for the velocity of the craft, that's already a violation because I mean, you could equate it to like moving down the road in a car. If you're able to throw a 90-mile-an-hour fastball, but then you throw a 90-mile-an-hour fastball from a car that's moving 100 mile an hour, you just threw a 190-mile-an-hour fastball. Well, if you're taking C, which is already the maximum speed of light, and you're adding anything to it, if you're adding the velocity of anything, which, the velocity of the GPS is significant, now it's greater than C. So the fact that they're even accounting for the velocity of the GPS satellite at all already is exceeding C and violating it. So I just wanted to make that distinction for the people in here who are, were thinking about that earlier, just to be clear, because that's like that's the first thing they do, and it's already violating their paradigm.
Dude, the satellite correction is so bad in their paradigm because they're explicitly like, oh, we can't measure Earth, it's in free fall, all this nonsense. And it's like, boys, you have a satellite falling around the Earth that you're correcting for its absolute velocity relative to the center of a coordinate system that you're using to describe its orbit. So you have a real problem here, homie. Like this is beyond the scope of relativity to explain, So it's so damn because the implication there is like, well, the Earth's free falling around the sun. Why can't we measure that? Oh, well, we can, but only with a Lorentz booster.
Hey, what's going on? Oh, just listen to you guys go at it. Hey, so is GPS satellites, are those really in towers on the ground or what?
So some of them are, but there's apparently some craft somewhere. They've got a network set up. They've got corrections based on the velocities of the like further movement and stuff. Now, are those the exact velocities that they say they are? Like we'll never know, right? But they are accounting for a moving satellite, or they're accounting for something carrying a clock that's moving, that's giving GPS signals. So
Interesting. I've always wondered how that worked.
yeah,
So what I'm trying to figure out is the towers make sense, right? They put it X, Y. Okay, there it is. It's a defined location that does not move, right? And you put another one, and then you can reference between those 2 points, and then a third one, and triangulate, and so on and so forth. What I'm trying to figure out is if if the signal is coming from the sky as well, how can they keep that like, is it
Got you.
moving? Is it stationary? And if it is
I got you,
stationary,
bro.
how does it stay in the same spot? You know, like, and if it does move,
Yeah.
then you know that's what
Yeah.
I get caught up in.
So for the stationary stuff, we're not we're not super sure. They say that it's at the equator, right? So we've got some ether explanations possibly to explain that, but again, that's all just like trying to explain things that may or may not exist in terms of the technology being there or like or how it's configured there, right? There could be balloons there doing a network around the equator. Who knows, right? But for how it works with moving systems, right? So let's say they have a balloon network and it's just balloons going back and forth, right? Taking different jet streams at altitude, doing circle loops or something like that, right? So they would have everything referencing the center of a coordinate system. So everything is going to. So if you take a look at this graphic here, look at the it's like a Gleason's map, right? And you have your 1, 2, 3, 4, 5. These are your positions of your satellites, and they're all referencing the center of the coordinate system, right? And then we have number 6 here, which is going to be a person that's going to try that needs to use the trilateration to tell where they're at on the coordinate system. So GPS sending the information when it sends its signal, it's saying, "Hey, I'm right here," in reference to the coordinate system. So it sends it to the observer here. He gets it, and his device determines based off of the input of all the other signals sent to it where it's at in reference to the coordinate system, based off of how long it took for those signals to get there or get to him.
Right. So it relies on a clock that is extremely accurate, so they know exactly how long, what the
Hmm.
latency is to each tower or signal, and then
Yep.
they just do
So
the
that
math and be like, okay, you're right here.
yep, and that's that's the point of having like atomic clocks in the so-called satellites. Like I said, whatever's carrying them around, they've got like 2 to 4 atomic clocks on them, so they can break a second down into 9,192,000,000ths of a second. So when they have that ability, like they got their accurate measurement, and then they use this equation, right, which is a range measurement equation. So they're just saying like they're taking a snapshot of the coordinates of when the signal was sent and when the signal was received, and then they just multiply that time interval by c, and the difference that they get out of that is the distance.
It's kind of incredible that that even works.
Dude, it's nuts, right?
Well, there's an additional layer of obfuscation that has to be baked into that none of us are going to be able to be privy to because, just as in Miller's experiments, he determined that the propagation rate changes based on altitude and time of year. They're also going to have to be accounting for that. And we're not going to even know what the true numbers are because they're just going to feed us this 20,000 kilometers away number or whatever, even though that's not the real number. So they're going to have these other variations they account for that we don't even know about. Like, so whoever actually codes this stuff is going to all obviously be privy to that and like just not telling the world.
Dude, well,
I mean,
just
it
what you
makes sense.
found. Sorry, go ahead. You're good.
I mean, it makes sense. I mean, just real quick, like if we could figure out the GPS location of all mobile cell phones, we would easily be able to prove if we're on a spinning ball or not just by the coordinate data alone, right? Because it'd be like, yeah,
It's operated by the military. The military is the ones that operate it.
yeah, because it would show people if you're in the United States, it would show people or America, it show people in Australia is upside down and um on the other side of the world, right?
I don't think it would work that way. You would you would get accurate distances to things. You would get true altitudes of the satellites. You would get the actual distance. So when it sends its coordinates to the receiver, you would have its actual distance for how high it is and the actual time of propagation, like without meridian corrections built into it. Because that's the other thing, right? It's like the the data's already been analyzed like on the back end. They already broad strokes sweep everything up under a SAGNet correction, under an additional SAGNet correction. You know, they're playing 3-card Monty with SAGNet corrections, and every fucking card is SAGNet correction to a row.
And that's another thing that I've been thinking about. That's been in the back of my mind, and I never really got around to looking into. Is that okay? All these GPS coordinates, you can just turn on your GPS. 20 seconds later, boom, you got your location like down to feet, right? And Google Maps like knows exactly where you are. You can do Street View, and if we're gonna say that no one has an accurate map, whether you believe in we're spinning on a spinning globe or a flat Earth or whatever, how how are they able to make it match perfectly? Almost, it seems like.
It's a great question. So for local for local use, right, it's going to be accurate, especially if you're in a city going to work, you're not going to notice any deviations. For larger distances, that's where they're going to be able to cook it in, right? So when people get into using things like GPS to verify reciprocal zenith angles and that kind of stuff, those distances based off of meridian corrections are always going to output the globe. Like you're always going to be able to use the coordinate system to travel from, across the country in America and shit. Like it's always going to be accurate enough for that, right? But if you were going to measure, if you want to take a single measurement from a location here based off of the time it takes to get to Florida or something like that, right? That distance, like that kind of stuff, is where the it's not going to be useful.
Interesting.
Because it's basically what they've got it, how they have it set, right? Is it's with the meridian corrections. They're just saying that based off of the amount of time, however much time they need to add or subtract to a measurement to get you the distance to put you on the coordinate system, on the globular coordinate system. That's all. That's all they're doing. It's already built in. It's just they're just adding time or subtracting it.
Bandana, bro.
Is that?
I'm digging the bandana, bro.
Oh, thank you.
Hell yeah. Sorry, I'm a little late. Just got back from the gym.
Good presentation, bro.
Thank you.
Interestingly enough, I went and asked ChatGPT about the Polaris referencing of the ICBMs at altitude, and it's sitting here telling me that that's not a thing, and as of its 2022 info, it doesn't know of any systems that use that. And I'm like, pretty sure Northrop Grumman does. Well, dude, I got a tour of the Northrop Grumman facility in Redondo Beach, California, and was like looking at their stuff. I got to see the James Webb Space Telescope before it got launched up. I got to the rundown about like the SR-71s and different stuff like that. I don't know if that's where I learned the stuff about the Polaris and the tracking or not, but I feel like it is. But I definitely definitely remember for sure that that there are ICBM systems that can self-track off of Polaris.
Well, we'll have to look into that later. So
Alright,
yeah,
any other?
yeah. Anyone else want to like bring anything else up before we close out stream, or any other comments, questions? Alan, you got anything else you wanted to say?
No, I think that's about it, man. I mean, we're looking at a long, extensive history here of trial and error, trying to fit relativity theory into technology that clearly doesn't need it. Um, and then, the surface level narratives that we get, like from the layman, is GPS proves relativity. GPS couldn't work without relativity. GPS is relativity. All these crazy things, and it's just like when you look into it, like everything else, not only does it refute relativity, it refutes the motion of the Earth, like all their mathematical presuppositions about motion. Like it's insane.
Yeah, and to bring it back to the twin paradox, right? Like if you're like me and you heard that at some point in your life and you thought like that just seems crazy, and the paradox like bothered you in an internal way, like I know it bothered me. That's because these things don't actually play out in reality, and your intuition that things in reality shouldn't play out that way is right. And that's like as Bennett pointed out, these things. That's what Bennett pointed out. That's what Ron Hatch pointed out. These things don't play out in reality, and Alan just showed you over and over and over and over again these things not playing out in reality. So there's no paradox. It's just Einstein was wrong. That's it. Over and done with.
No, but just trust the math that wasn't even presented. Yeah. All right, cool. So if there's no further questions, comments, I think I'm good to end out if you are.
Yeah, let's close it out.
All right, cool.
Thanks everyone for listening in. It's been an etheric time.